previous lecture, we were describing Taylor's expansion or Taylor's approximation of a function of several variables. In writing Taylor's expansion, we have got to know two particular notations. Those are small o and big O. With the help of those two notations, we have described how to write Taylor's linear approximation and Taylor's quadratic approximation of a function of several variables. With the idea of Taylor's expansion, we have finished the portion of required tools from calculus for functions of several variables. Now in this lecture, we will start a new unit, the unit 3 of the course, on the topic of convex functions and convex sets. Neatly, in this lecture, at first I will discuss what do we mean by a convex set, then a few commonly occurring convex sets in optimization will be described. Finally, we will get to know a few convexity preserving operations. You know, convexity plays an important role in any optimization problem of a function of one or more variables, because you note that if I have a function of several variables that has a local minimum, say at x bar, then roughly there is a local neighborhood of the point x bar where the graph of the function has a bowl or vessel type structure. By that we mean the function f is convex in a local neighborhood of the point x bar. For example, if I consider a function of one variable and say the graph of the function is somewhat like say this one, then in a local neighborhood of this local minimum, say the point x bar, we see that the graph of the function inside this small neighborhood of the point x bar is convex in nature. Optimization problems with convex functions, you know, is one of the biggest success stories of modern theory of optimization. By convex optimization, I mean a minimization problem, minimization of a convex function subject to a convex constraint, that x belonging to a convex set, say capital C, in a structured manner. This set capital C is presented by some inequalities given by a few convex functions, say gixs less than equal to 0 for I is equal to 1 to m, and equality constraints are given by some linear functions aj transpose x is equal to bj for j is equal to 1 to till k say. You know, in presenting constraint sets, these inequalities appear so often that Professor R.T. Rockefeller, one of the giants in convex optimization, says that inequalities are hallmark of modern optimization. You know, particular cases of this convex optimization problem has numerous important applications in practical or theoretical optimization problems. For instance, problems from automatic control, network flow, resource allocation, or portfolio optimization are applications in engineering, wide application of linear programming problem in operations research, and support vector machine problems in machine learning are special cases of these general convex optimization problem. And you know, convex optimization problems are pretty much broadest class of optimization problems that we know how to solve efficiently. In fact, there is available toolbox in different softwares like AMPL or in MATLAB to handle convex optimization problems effectively. Today, the collection of techniques to solve convex optimization problems effectively is so vast and elegant that Professor Stephen Boyd from Stanford University mentions that convex optimization techniques are almost going to be reliable technology. By reliable technology, we mean just you feed the methods of convex optimization into your machine and machine will reliably and effectively solve your practical convex optimization problem. In this lecture and in next few lectures, maybe 3 to 4 lectures, we shall discuss the notions of convex sets and convex functions. Let me at first define what do we mean by a convex set. A subset of Rn, say capital C, is said to be convex if for any pair of points, say x and y, inside the set capital C, the line segment joining these 2 points x and y also lies inside the set capital C. That is, for any given lambda in between 0 and 1, the point lambda x plus 1 minus lambda into y belongs to the set capital C. You know, this expression lambda x plus 1 minus lambda y is called a convex combination of the points x and y. For a given finitely many points, say x1, x2 till xp in Rn, the expression of the type summation lambda I into xi for I is equal to 1 to p, where lambda i's are real numbers with all of their sum is equal to 1 together with all lambda i's are non-negative, is called a convex combination of the points x1, x2 till xp. For example, if we have, let's suppose, 3 points x1, x2, x3 from the R2 plane, then this expression, say 1/3 x1 plus 2/3 x2 or 1/4 x1 plus half x2 plus 1/4 x3. These two expressions are convex combinations of the points x1, x2 and x3. Now let me give you a few examples of convex sets that commonly occur in optimization. The first example that I would like to give is a hyperplane, which is usually presented by set of all points in Rn such that a given constant vector in Rn, say the vector p, its transpose times the general vector x is equal to a scalar alpha. Here this vector p is a non-null vector and alpha is a real number. This set geometrically in R2 plane is a line given by the expression p1 x1 plus p2 x2 is equal to some scalar alpha. Here p1 p2 are two real numbers. In R3 space, this set gives us a plane, and in R4 or more than three-dimensional spaces, this set represents a surface what we call as a hyperplane. It is very easy to check for this set to be convex. You just pick up 2 points from this set and just show that their convex combination is belonging to this set. That means you just take, let's suppose, x and y belonging to this set denoted by, say, capital H, and so that for any given lambda inside closed 0 to 1, the expression lambda x plus 1 minus lambda y belongs to the set capital H. Next, with the help of a hyperplane, we will consider one half side of a hyperplane. By that we mean a closed half space is also an example of a convex set. A closed half space in Rn is presented by P transpose x less than equal to alpha, where this vector P is a non-null vector and alpha is a real number. Geometrically, a closed half space in R2 plane gives us the region that is one half side of a line. A polyhedral region, which is defined by intersection of a finitely many closed half space, is also an example of a convex set. A polyhedral set mathematically presented by set of all points in Rn that satisfies finitely many inequalities of this type. That is, let's suppose pi transpose x less than equal to alpha I, where pi's are non-null vectors in Rn and alpha i's are real numbers. As a next example, I would like to consider Euclidean ball, which is given by set of all points in Rn such that the Euclidean distance from the point x to a given point A is less than equal to some non-negative number, say r, where A is a given point in Rn and r is a real number greater than equals to 0. This set is an example of a convex set. We all know that this set geometrically gives a circle in the R2 plane if the location of the point A is over here. Then the collection of all points which are inside the circle of radius r presents this particular set, and you notice that you pick off any two points from this set and then consider the line segment joining those 2 points. This line segment entirely lies inside this particular set, and hence this set is a convex set. An Euclidean ball in 3D space is a spherical ball. Instead of considering here this Euclidean norm, we might have also considered any other norm, and we will be able to realize that with respect to any other norms over here is also a convex set. Here then let me give you a home task that you prove that with respect to any norm in the n-dimensional Euclidean space Rn, this set norm of x minus a less than equal to a non-negative quantity is a convex set. Let me also put off one more home task over here, that consider a positive definite matrix of order n by n and then consider the collection of all points x's which are satisfying x minus a transpose multiplied with a positive definite matrix, say capital P, into x minus a less than equal to r for a non-negative real number r is also a convex set. Here a is a priori given point in Rn and r is a real number greater than equals to 0. Geometrically in R2 plane, you can quickly identify that this set represents an elliptical region, and in 3D space when n is equal to 3 over here, then this set gives an ellipsoidal ball. This ellipsoid is also an example of a convex set. In the next, I will consider an example of convex cones, whereby a cone in Rn we mean a non-empty set, say capital C, that is closed under positive scalar multiplication. By that I mean whenever a point x is lying inside the set C, then for any given non-negative scalar lambda times x is also belonging to the set C. We can quickly find that if I consider a region in the R2 plane that lies in between, say, this ray and this ray, that is, we are considering this region in between these two particular rays, then we see that this dotted region is a cone. Because you consider any point inside this set, then you consider any non-negative multiplication of this point, which will give us a vector of this type. Whatsoever lambda greater than 0 you choose, all these lambda x's are inside the set, and therefore this region is a cone. Notice that I could have considered union of two such figures. For instance, I consider union of this dotted region with another cone, say given by the region in between this ray and this ray, that is this dotted region. Then we see that union of these two dotted region, this region and this region, is also a cone. That means if I just write this set as S1, this dotted region, and this dotted region as S2, then you notice that S1 union S2 is a cone. Here you notice that individually these two sets S1 and S2, they are convex sets, but this union S1 union S2 is not a convex set, because you pick up a point from S2 and a point from S1, then you notice that this line joining these 2 points is not entirely lying inside the set S1 union S2, and therefore this S1 union S2 is not a convex set. A set that is cone as well as convex is called a convex cone. Let me give you a few examples of convex cones. The non-negative orthant in Rn space, that is the set of all points in Rn whose all components xi's are non-negative, is an example of a convex cone. This set, which we commonly denote by Rn plus, is a cone as well as a convex set. The norm cone or the ice cream cone or the Lorentz cone, which is given by the set of all points in Rn plus 1, where x is an element in Rn and t is a given scalar or a real number, for which with respect to a given norm in Rn, norm x is less than equal to t, is a convex set. This is very easy to verify, that you consider any pair of points from this set, that let us take x1 t1 and x2 t2 belonging to this set capital S. That is, we are considering norm x1 is less than equal to the real number t1 and norm x2 is less than equal to t2. Then we notice that for any given lambda greater than equals to 0 and less than equal to 1, the norm of lambda x1 plus 1 minus lambda x2 is less than equal to, by triangular inequality, lambda times norm x1 plus 1 minus lambda times norm x2, which is further less than equal to lambda t1 plus 1 minus lambda t2. And therefore we see that the point lambda x1 plus 1 minus lambda x2 together with lambda t1 plus 1 minus lambda t2, this point is belonging to the set capital S, and hence lambda times this point x1 t1 plus 1 minus lambda times the other point x2 t2 is belonging to the set S, and this is happening to be true for any choice of lambda in between 0 and 1, and therefore the set capital S, which we call as norm cone, is a convex set. This set S is called a cone because you just pick up any point xt from this set S and then you multiply by a non-negative scalar lambda. You can trivially show that lambda times xt is also belonging to the set capital S. Thus this set is a cone. Another example of a convex cone is the cone of all positive semi-definite matrices, which we call as positive semi-definite cone. We denote this set of all positive semi-definite matrices of order n by Sn plus, which is the collection of all matrices of order n by n that are symmetric and positive semi-definite. I am again here keeping a home task that you please prove that this set Sn plus is a cone as well as a convex set. Now next I will move towards mentioning a few operations that preserve convexity. Towards this I start with a question. Let's suppose we are given two sets, say S1 and S2, which are both convex. I ask you whether their union and intersection are convex sets. You have already gotten enough hint that S1 union S2 might not be a convex set even if S1 and S2 are convex sets. You can simply take off two convex sets in R2 plane. Let's suppose you just consider, say, a circular ball and an ellipsoidal ball, which are both convex, but we notice that their union is not convex. Now what about the intersection of two convex sets? Intersection of two convex sets is always a convex set. This result is very trivial to prove. You consider any pair of points from S1 intersection S2. Their convex combination is lying in both the sets S1 and S2. Therefore, intersection of two convex sets is a convex set. You know, to obtain convex sets from union, we can take convex hull of the union of two convex sets. By convex hull of a given set, capital S, we mean the set of all convex combinations of the elements of the set capital S. For example, if I consider the set capital S consists just say 3 points in R2 plane, say these 3 points, then the set of all convex combinations of these 3 points will construct the triangular region having vertices as these 3 points. Set of all convex combinations of these 3 points is this triangular region. If I consider the points on a circle in the R2 plane, say this circle, then we'll find that the convex combination of all the points in this circle is this entire disk type region. Set of all points, those are lying on and inside this circle. You know, for intersection of convex sets, not only intersection of finitely many convex sets, but also intersection of any arbitrary family of convex sets is a convex set. Now next, for convexity preserving operation, I would like to consider Minkowski sum and Cartesian product of two convex sets. The result neatly states that if I have two convex sets, say S1 and S2, then all the following sets are convex, where in the following we will consider at first the set given by the Minkowski sum of S1 and S2, which is defined by set of all points x's in Rn such that x can be presented by addition of a point x1 in S1 and x2 in S2. Next, the set given by S1 minus S2, that is the collection of all points x's in Rn such that x can be presented by difference of an element in S1 and x2 an element in S2. Cartesian product of S1 and S2 is also a convex set. A scaling of a convex set, by that I mean you consider any real number, say alpha, and consider the set alpha S1 given by the collection of all vectors of the type alpha multiplication of x's, where x is belonging to the set capital S1. This set is called a scaling of the set capital S1. Scaling operation of a convex set also gives us a convex set. A translation of a convex set is also a convex set. By translation of a set, we mean for a given vector, say P in the n-dimensional Euclidean space Rn, this P translation of the set S1 is defined by collection of all points of the type x plus p where x is in the set capital S1. This translation of a convex set is also a convex set. Next, I would like to mention that push forward by an affine map and pull back by an affine map of a convex set are also convex. Let me neatly write the result over here, that push forward by an affine map of a convex set gives us a convex set. For the result to be stated neatly, let me consider an affine map, say capital F, from Rn to Rm, and let us suppose we are given a convex set in Rn, say capital S. Then the set, the image of capital S under the function f, that is the collection of all vectors in Rm that are given by fx, where x is inside the set capital S, is a convex set. Notice that this set can be also presented by the expression of the affine map capital F. As capital F is an affine map, we all know that the expression of the function f can be presented by fx is equal to a linear transformation, say capital Ax, plus a constant vector, say w. Here this capital A is a matrix of order m by n and w is a vector in the Rm space, that is w is of dimension m by 1. And thus this image set Fs can be presented by set of all points Ax plus w, where x is inside the set capital S. We can easily prove that if the set capital S is convex, this set Fs is a convex set. I am keeping it as a home task. Pullback or a preimage of a convex set by an affine map is also a convex set. Let me write it neatly over here, that pullback by affine map of a convex set is also a convex set. For this to be stated neatly, let capital F be an affine map from Rn to Rm, and let capital S be a convex set in Rm. Then the preimage of capital S under the function f, which we denote by f inverse S, that is the collection of all vectors in Rn for which FV is in the set capital S, is a convex set. I will not again prove this result. You please figure out the proof for this result. It is again a bit trivial. I will rather give you two examples where we will try to visualize this push forward and pull back of convex sets by affine maps. We consider the first example as an example of push forward that consider, say, the unit ball in the R2 plane. That is the collection of all points x1, x2 in R2 such that x1 square plus x2 square is less than equal to 1. This we all know is a convex set. Now we consider an affine map from R2 to R2 given by f of x1, x2 is equal to a 2 by 2 matrix, say 2 1 1 2 times the vector x1 x2 plus a constant vector, say 1 1. Here geometrically the set capital S we all know is a circular disc, say this disc having radius 1 centering at origin. Now let us try to identify the collection of all elements in the set Fs. Notice that Fs is given by set of all points in the codomain space, that say y1, y2, for which there exists a point x1, x2 in S, for which fx1, x2 is equal to this y1, y2. That is, y1 and y2 are given by this first component of this expression, that is 2x1 plus x2 plus 1. Y2 is the second component of the expression of fx1, x2, that gives us x1 plus 2x2 plus 1. But here this x1, x2 are to be taken from the set capital S. So we must have x1 square plus x2 square is less than equal to 1. Now you please note that if I go for solving these two equations in terms of x1 and x2, then we will find that x1 is given by 1/3 of 2y1 minus y2 minus 1, and x2 is given by 1/3 of 2y2 minus y1 minus 1, and hence the set capital S is the collection of all y1 y2's, for which we have square of this expression plus square of this expression is less than equal to 1. That is, we have 2y1 minus y2 minus 1 square of it plus 2y2 minus y1 minus 1 square of it is less than equal to 9. You can figure out that if S is given by an elliptical region whose boundary is an ellipse of this type, where the center of the ellipse is at the point 1, 1. Collection of all points inside this ellipse is the image of this circular region under the affine map capital F. We notice here that this image Fs of the convex set S is again a convex set. Now I will consider an example on pullback of a convex set by an affine map. We consider the set capital S a convex set. We simply consider, say, a convex set in the real number line, that is an interval, say 1 to 4, and we consider a real valued affine map defined on the R2 plane, that is given by, say, f x1 x2 is equal to x1. Then we see that the set F inverse S, the pre-image of the set capital S under the function f, is the collection of all points x1 x2 in the R2 plane, for which f x1 x2 is belonging to the set capital S, which is given by then the set of all points x1 x2 in the R2 plane, for which x1 is lying inside the set S, and therefore x1 is in between 1 and 4, which gives us geometrically an infinite strip in the R2 plane. This infinite strip is identified by these dotted points in between these two lines is the set F inverse S. We notice that this set F inverse S is a convex set. Now I will end up this lecture by mentioning one more convexity preserving operation, that is the push forward and pull back by perspective map of a convex set. By a perspective map we mean a function that is defined as follows, that we consider a set, say capital D, that is collection of all points xt's, where x is lying in the Rn-1 space and t is a real number which has positive value. In this set capital D, we define a function, say small f, given by f of xt is equal to 1 upon t times x, that is explicitly is equal to, in the first component we have x1 by t, in the second component we have x2 by t, and in the n-1th component we have, where this x1 x2 till xn minus 1 constitute this vector x. This function f is called a perspective map. Now I will show that image of a convex set by a perspective map is again a convex set, that is pushed forward by a perspective map of a convex set capital S, which is a subset of the set capital D, is a convex set. The proof of this result is not trivial and a bit constructive. Let me prove this result. Note that the set Fs is given by the collection of all points, say Ys, in Rn-1, for which there exists a point xt in the set capital S, for which f of xt is equal to y. That means y is equal to 1 by t times the vector x. Now to prove this set Fs to be convex, let us consider any pair of points, say y1 and y2, inside the set Fs, and let us pick any real number lambda in between 0 and 1. We will show that lambda y1 plus 1 minus lambda y2 is inside the set Fs. To prove that lambda y1 plus 1 minus lambda y2 is inside the set Fs, we need to find a point, say x dash t dash, inside the set capital S, for which this lambda y1 plus 1 minus lambda y2 can be expressed by x dash divided by the real number t dash. Let us now try to figure out some expression of this x dash and t dash. Now we see that this expression lambda y1 plus 1 minus lambda y2 is given by lambda times x1 by t1 plus 1 minus lambda times x2 by t2, where this x1 t1, this coordinate is such that f of x1 t1 is equal to the vector y1, and this coordinate x2 t2 is such that f x2 t2 is equal to the vector y2. Existence of this x1 t1 and x2 t2 is possible because these y1 and y2 are elements from the set Fs. So there exists x1 t1 inside the set S and x2 t2 inside the set S, for which we have these two equations, fx1 t1 is equal to y1 and fx2 t2 is equal to y2 are valid. Now a simplification of this expression is given by 1 over t1 t2 times lambda t2 into x1 plus 1 minus lambda t1 into x2. Now here, as t1 and t2 both are positive, this t1 t2 is positive certainly. So we can think of this t dash over here, which we are searching for, can be taken as t1 into t2. But what about this x dash? Can we take this expression as x dash? But what is the guarantee that this expression can act as x dash, so that this x dash t dash is inside the set capital S? So a simplification of this type may not give us a straight way to identify a point x dash t dash inside the set S, for which this entire expression can be expressed by x dash divided by t dash. To identify then a point x dash t dash which satisfies this requirement, let us now try to see if we can express the expression lambda y1 plus 1 minus lambda y2 by 1 over some t dash. We will find later what would be a possible t dash, but we multiply it with a convex combination of x1 and x2. If we can assure existence of a theta in between 0 and 1, for which this equation is valid, then you notice that we can go with this expression as our x dash, and that will serve our purpose. Now here I would like to give you a home task, that verify with theta is equal to lambda t2 divided by 1 minus lambda into t1 plus lambda t2. We have lambda x1 by t1 plus 1 minus lambda x2 by t2 is equal to theta x1 plus 1 minus theta x2 divided by t dash as the element, theta t1 plus 1 minus theta t2, and hence we see that this element theta x1 plus 1 minus theta into x2 together with theta t1 plus 1 minus theta t2, which is a convex combination of the points x1 t1 and x2 t2 and hence belonging to the set capital S, is such a point that taking up this expression as x dash and this expression as t dash, we have x dash over t dash is equal to the expression lambda y1 plus 1 minus lambda y2, and therefore this lambda y1 plus 1 minus lambda y2 is belonging to the set Fs. This proves that the set Fs is a convex set. Now I would like to mention another result, that pullback of a convex set by a perspective map is again a convex set. If we consider a set, say capital S, a convex set in Rn-1, and we have a function f that is a perspective map, then the preimage of capital S under the function f is a convex set. Now, although this result is not a bit trivial, but I would like to keep it as a home task, that you play with the variables, convex sets and perspective map and try to figure out the proof of this result. I positively hope that you will be able to do it. Now, as an application of this image under perspective map, I would like to give another home task here, that you show image of a convex set by a linear fractional map is again a convex set. By a linear fractional map, we mean an expression of the type if x is equal to ratio of two expressions, those are an affine map ax plus b and a scalar c transpose x plus u, where here I consider A to be a matrix of order m by n, x is a variable in the n-dimensional Euclidean space, b is a vector in the m-dimensional Euclidean space, c is a given constant vector in the n-dimensional Euclidean space, and u is a real number. Now on the set, say capital D, which is a collection of all points in the n-dimensional Euclidean space for which C transpose x plus u is greater than 0, this function f from the set D to Rm having this expression is called a linear fractional map or a linear fractional transformation. Now you show that if we consider a convex subset of the set capital D and a linear fractional transformation, say f defined on D, then the set Fs is a convex set. Therefore, a push forward of a convex set by a linear fractional map is again a convex set. The proof of this result is not trivial. I will just give a sufficient hint, that you please try to write the function fx as a perspective map of an affine transformation, say G. You find a suitable expression of this G that is an affine map whose perspective is the function fx. You can quickly identify what is this expression of Gx. Let me just give you that Gx can be presented by the matrix capital A in small f, and in the down you please write C transpose multiply with x plus the vector b and u over here. You please look at the expression of f given by ax plus b divided by c transpose x plus u. Then you collect a, c, b and u, form this function gx, which is an affine map. Now notice that this function small fx is the perspective of this function gx. Now next you try to employ the results that I have stated so far in this lecture, and then try to figure out why pushed forward by a convex set by a linear fractional transformation is a convex set. With this, I end up this lecture here. In the next lecture, I will try to consider results on separating a point and a given closed convex set in the n-dimensional Euclidean space. Thank you. Thank you all for all of your kind attention.